Moment of a force. The moment of a force about a point is the product of the force and the perpendicular distance from the line of action of the force to the turning point. Moment of a force is a measure of the turning effect of that force. Shown above is a simple illustration of a body PQ supported maybe with a knife edge represented by letter K, and a perpendicular force acts on it at a distance d from the knife edge. Here is the statement. For a body PQ which is supported at K and a perpendicular force F acts on it as shown, the moment of the force about the turning point, that's K, is equal to the product of the force and the distance from the force to the turning point. The unit of moment is Newton meter. The principle of moment states that the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. The conditions for the equilibrium of a body under the action of parallel forces are 1. Sum of the forces in one direction is equal to the sum of the forces in the opposite direction. Or, can be stated, the algebraic sum of the forces on it is 0. 2. The sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. Or, the algebraic sum of the moments about the turning point is 0. The center of gravity of a body is the point where the resultant weight acts or concentrates or appears to concentrate. For a uniform meter rule, beam, rod, etc., the center of gravity is at the midpoint of its length. A couple is a system of two equal but opposite forces whose line of action does not meet, as illustrated in the diagram below. The forces F, they are equal, and the distance between them, they act on this body. The moment of a couple is the product of one of the forces and the distance between them. Example 1. A uniform rod PQ of length 1 meter and mass 2 kg is pivoted at the end P. If a load of 14 newtons is placed at the center of the rod, find the force that should be applied vertically upwards at Q to maintain the rod in equilibrium horizontally. A, 68 Newton, B, 28 Newton, C, 17 Newtons. and D 7 Newton. The solution is as follows. Let the rod PQ be represented by this line. Here is P, this other end is Q. According to the question, we are told that it's pivoted at P. There is a support here. And because it's a uniform rod, the center of gravity, where the weight of the rod concentrates, is at the midpoint. This is our center of gravity. Here we have the weight of the rod. The weight is mg, and that gives us 2 times 10. The weight of the rod is 20 Newton. And from P to the center of gravity is 0.5 meters, because the center of gravity is at the midpoint. And from this center of gravity to the end Q is 0.5 meters. The entire length of the rod is 1 meter. We are told in the question that an extra load is placed at the midpoint. If an extra load of 14 Newton is placed at G, then the real diagram is of this form. This is the center of gravity. Here becomes 20 plus 14, giving us a total load of 34 newtons here. Here is P. This is the support. Here is Q. Then the question is for us to get the value of the upward force at this end that will make the rod to balance horizontally. Let's put our dimension 0.5 meters from the diagram above. Taking moment about P, the turning point where we have the support, we apply the principle of moment, clockwise moment, about P must be equal to anti-clockwise moment about that same point called P. If we take that, our clockwise moment about P is 34 times 0.5. Our anti-clockwise moment about P will give me F times 1. 17 is equal to F. So the upward force that is needed to maintain the rod horizontally is 17 Newton. Option C is therefore correct. Example 2. A uniform light beam XZ is hinged at X and kept in equilibrium by the forces T and F as shown in the diagram below. If XO equal to 20 cm and OY is equal to 30 cm, express T in terms of F. And this is the diagram we are to consider. Option A, T is equal to 2 root 3F divided by 3. B, T is equal to 2F. C, T is equal to 5 square root of 3F divided by 3. And D, T is equal to 5F. The solution is as follows. You have to note that the moment of a force about a point will come into effect only when the force meets the body at angle 90 degrees. The force T is inclined on the body at an angle of 30 degrees. So the first work to do is to get the vertical component of that force. We have force T at angle 30 degrees on this body. For us to get the vertical component of force T is T sine theta. That will give us T sine 30. So that vertical component is 0.5 T. Then we can withdraw. Our beam is now like this with a vertical force called 0.5 T. That's the value of the vertical force. And this point X, where it's hinged, then we still have a force F at a point Y, which is 30 cm from the 0 point. From X to that 0 point is 20 cm. Then this last end is Z. We can now take our moment about the point where the beam is hinged, point X. Therefore, clockwise moment about X must be equal to anti-clockwise moment about that same point X according to the principles of moment. Force F will turn the beam XZ clockwise. So the moment of F about X is F times this distance, which is 50. 30 cm plus 20 cm. So we have this moment as F times 50. Then the second force, the 0.5 T that pulls it up vertically, is turning it anti-clockwise about X. So the value is the force, which is 0.5 T, times the distance from that point to the turning point, which is 20 centimeters. So we have 50F is equal to 10T, which means T is equal to 5F. Therefore, option D is correct. Example 3. A uniform beam PQ of mass 20 kg and length 5 meters is balanced as shown below. A man of weight 800 Newton stands at M such that QM is equal to 2 meters. The reaction at P and Q respectively are dash. And this is the diagram. Option A, 220 Newton and 380 Newton. B, 380 Newton and 220 Newton. C, 420 Newton and 580 Newton. And D, 580 Newton and 420 Newton. Solution. Let the beam be represented by line PQ. So this is our beam. The man is standing at a point M. The weight of the man is vertically downwards, and that weight we are told is 800 Newton, and is at a point 2 meters from end Q. Being a uniform beam, the weight of the beam itself is at the midpoint. The midpoint of 5 is somewhere here. This is the center of gravity G. The midpoint is here. And the weight is 20 times 10. Weight is 200 Newton. Let's not forget that the weight of the beam is mg. So that you have the mass times 10. That's how I got the 200 Newton. I fixed there. And from here, that point, the center of gravity to NP is 2.5 meters. Then the question. We have to find the reactions at P and Q. Yep, this point is M. Reaction is in the upward direction. This reaction at P. And this is reaction at Q. We have something like this as the second force called the reaction. Then we apply the principles of moment. The first condition for the equilibrium of this body is that the sum of the upward forces is equal to the sum of the downward forces. Since the beam PQ is now in equilibrium under the action of parallel forces, the two conditions apply here. One, the sum of the upward forces, sum of upward forces is equal to sum of downward forces. By this we mean the upward forces are the reaction RP plus reaction RQ should give us 200 plus 800, which are the downward forces. RP plus RQ should give us 1000. This is equation 1. Second condition is sum of clockwise moments about a point, let's say about P, must be equal to sum of anti-clockwise moments about that same point P. When we take our moments about that point, we have the clockwise moments as 200 times 2.5 plus 800 times 3 should be equal to the anti-clockwise moment RQ times 5. 500 plus 2400 should give us 5 RQ. 2900 is equal to 5 RQ. RQ, the reaction at point Q will give us 2900 divided by 5. And that will give us 580 Newton. But RQ plus RP is 1000. Now we know RQ to be 580 plus RP is giving us 1000. Therefore, RP is 1000 minus 580, which is 420 Newton. Option C is correct.